We'll be solving one more problem by dynamic programming. This problem is referred as reliability problem, right? So in this problem, an electronic circuit is to be devised by using three components A, B and C. As you see here, the electronic circuit is to be devised by using three components A, B and C. Now these components are connected in series, right? For example, like this one, this is B and this is C, right? A, B and C are connected in series. Now each component has its own reliability. For example, say the reliability of component A is zero point 0.7, reliability of component B is 0.5 and reliability of component C is 0.6, for example. So the resultant reliability of complete circuit, right? Reliability of complete circuit will be zero point 0.7 into zero point 0.5 into zero point 0.6. So that comes out to be whatever it comes, you just find that out, right? So reliability is found by multiplying. This is the first thing you keep in mind. While we proceed through this problem, you will need this particular concept. Now, this circuit used to be devised in 100 rupees, and you need to get maximum reliability. You want to maximize the reliability of electronic circuit. All right. So, um, one more thing. If the number of units of certain component are banked, are combined, and then the reliability of that particular component increase. There is a logic in the bank that, for example, here is a product A. Now, three units of product A will be present in that part. For example, this is called as three component bank. Okay, one component, one unit of A, simply one unit of A will be costing rupees 10. For example, it will be costing less, and as we combine more units of that particular component, then the cost of it will increase and also the reliability will increase. So what happens, just look here. For example, say there is 3 unit bank of component A, 2 unit bank of component B, and say 3 unit bank of component C. There is a logic by which these components will be coming in circuit in sequence, right? It will be happening something like this. If this fails, this will become active and it will get connected to component B. And if suppose say this fails, this will become active and the device will still continue to work because of the logic that this component will now be connected to B. This is the way it works. And because of this, if you have more number of units of certain component in the bank, then the reliability increase, and for higher reliability you have to pay more, right? So in this table, you have been given the reliability of component A for 1 unit bank, 2 unit bank, and 3 unit bank. The reliability, as you are seeing, is zero point 0.7, zero point 0.8, zero point 0.9. Reliability is increasing, and the cost is also increasing 10, 20, and 30. It is not necessarily increasing linearly. Okay, it could be anything 10, 20, 35, right? So component B, 1 unit bank reliability is zero point 0.5, 2 unit bank reliability zero point 0.7, and zero point 0.8 for 3 unit bank. The cost is 20, 40, 50. And likewise for component C, reliability increases to zero point 0.6, zero point 0.7, and zero point 0.9 respectively for units 1, 2, and 3 in bank of component C. All right. Cost accordingly is higher, increases from 20 to 30 to 40. All right. So we will now be seeing uh, how this is handled by dynamic programming. All right. Minimizing this. Okay. So in stage one, I'll be considering only item A in design of circuit. Okay, only item A, and it is implied that one unit must be there of any component in the circuit. Otherwise, if there is no unit of that particular component, may it be A or B or C, if the unit of any particular component is not present or it is present in zero number, then that circuit will not work. So now our stage is for component A. Okay. Then here are the alternatives. These are the states. Okay, so what will be the states? Now, as you know, states are the assumed limit of the constraint. I have the limit of 100 rupees. I have to design the circuit in 100 rupees. It should not cost more than 100 rupees. So what I'll be doing, I will be taking this constraint limit. I'll be assuming various constraint limit like 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Why? Well, again, you should answer to yourself why I'm not taking 5, 15, or 17. Because when you refer to the money part of cost part of each of the component, you see here that the costs are in multiples of 10. Okay, in multiples of 10, so you can safely take the states in multiples of 10, right? So I have taken 10, 20 to 100. Then what are the alternatives? First alternative is have one unit component of A. The cost is 10 and the reliability is zero point 0.7. Here again, my objective is to maximize the reliability, and that is why I am writing the reliability term at the end. Okay, so the first thing which appear in the alternative is number of units present in the bank. There is one, then the cost, and then the reliability. So second alternative, have 2 unit bank of component A. The cost is rupees 20 and the reliability is zero point 0.8. And likewise, the third alternative, have the 3 unit bank. 3 unit bank, the reliability is zero point 0.9, which is to be written at the end, and the cost is rupees 30. Okay. Now that you have written the alternative and the states, 70% of the task is done. Right. Now that you will be choosing alternative one, first of all, you have to check whether you are able to choose alternative one or not. Yes, you are able to choose because that alternative one requires rupees 10 only. And you have assumed that you have rupees 10, and that's why you have assumed that you have rupees 10 or more, as you see in this column. So all throughout in this column, the reliability will be zero point 0.7 because you are choosing this alternative. Now coming on to second alternative is available to you if and only if you assume that you have more than rupees 20, and therefore this alternative is not available when the state is 10. And also this alternative is not available when the state is 10. Third alternative is not available. Why? Because that third alternative requires minimum 30 rupees. Requires you to have 30 rupees, right? Or more. So if you have more than 20 rupees, 20 or more, the reliability or the return will be 0.8 throughout, right? And then here, if the alternative you are able to choose, then the reliability will be zero point 0.9. And lastly, you are collecting optimal return for each of the state. For if the state is 10, the reliability, optimal reliability you can get is zero point 0.7. If the state is 20, 0.8. And after the state is 30, the reliability is zero point 0.9. There we complete the first stage computations. Then we will be considering in our circuit, we will be considering B along with A. Okay, so B along with A. So come here, going to second stage. Okay, right. So here you may wonder why I am taking the stage from rupees 30 to 100. Okay, there is a reason for that. If I take rupees first stage of rupees 10 only, then what may happen? The this component B is costing me rupees 20. So there is no question that I will be having component B in my circuit because it costs rupees 20. And if I am having just rupees 10, then I can't have any unit of B. So there is no meaning if you take the state of rupees 10, and there is no meaning if you take the state of rupees 20. Why? Because if you have the state of rupees 20, then what will happen? You will be having one unit of product B, component B, and there won't be any money remaining to purchase any unit of any unit component bank of component A. So what you should do, just look here. What you should do, that when you come to component B, the minimum amount which you will be needing at your disposal should be 10 for one unit of component A and 20 for one unit of component B. Minimum 30 rupees is required. Then only you can devise a workable circuit, right? So your states are starting from 30. Okay, it will continue to 100. All right, 30 to 100. An alternative just discussed, your first alternative for component B only, one unit component bank for one unit bank for component B cost rupees 20 and reliability is 0.5. Two unit bank for component B cost rupees 40, reliability 0.7, and 3 unit bank cost rupees 50 and reliability 0.8. So now, if you are 30 rupees, obviously you are able to choose first alternative. Okay, because that first alternative requires you to have 20 rupees and you are having 10 rupees. You are having 30 rupees. All right. So you are having 30 rupees and 20 rupees spent in component B. Okay, giving you the reliability of zero point 0.5. Okay, so first component of the return is zero point 0.5, and the second component will be the remaining value, the value of state remaining after consuming the state, some amount of state for the alternative. Okay, you had the state value 30, and you have consumed 20 rupees for first alternative, 10 rupees are remaining with you, and in that 10 rupees, the best reliability you can get from previous stage is this one you see here. In 10 rupees you are getting best reliability of 0.7, right? You just remember this figures zero point 0.7, zero point 0.8 and zero point 0.9 and there onwards, because I won't be changing the page again. Okay. Now, if you assume that you have 40 rupees, you have consumed 20, and 20 rupees are remaining with you, and in that 20 rupees, you will be having two component bank. Or optimal return into 20 rupees is coming out to be zero point 0.8 from previous stage. Okay, one more thing you should mark here. Here you are not adding the reliability, because real reliability, because the components are connected in series, and reliability is that way probability. Okay, probability that the component will work, and these probabilities are to be multiplied to get the resultant probability. So here you don't have plus sign, you have multiplication sign. All right. So zero point 0.5 into zero point 0.8, and likewise zero point 0.5 into zero point 0.9, zero point 0.9, zero point 0.9, and so ahead. Okay, it will be 0.45 ahead, right? I have not written here, um, but there is no point, there is no problem in writing the values ahead. Okay, so all these values, however, will be 45.45. All right. Now, second alternative, I cannot use the second alternative until I think I have 40 rupees. How many rupees? 40 rupees are required just for component B. Okay, 2 unit bank of component B, and after you consume 40 out of 40, from where you will purchase at least 1 unit of component A, at least 1 unit bank of component A. That is not possible. Okay, these considerations you will have to do. So manual intervention is often required while having the planning of dynamic programming. Okay, in simplex method, once you give the formulation to the simplex method, it will get you the solution. But here, in the initial planning of the dynamic programming, human intervention is required. Okay, so 40, because you need minimum 50 rupees for having a workable circuit with which will have 2 unit bank of component B. Okay, I hope you have understood this. So 50 minus 40 is 10 rupees will be balanced with you, and within that 10 rupees you can get the reliability due to component A zero point 0.7, reliability due to previous stage of 0.7, and then again 60 and 40, you will have 20 rupees balance with you, within which you can get the reliability of 0.8, and then 30 rupees will be balanced with you, then 40 rupees will be balanced with you, 50 and 60 rupees will be balanced with you. For all those cases, the reliability from the previous stage, optimal reliability from the previous stage for remaining value of the state is zero point 0.9, and this is the result I have written here. And likewise for the third alternative, the minimum cost for three component bank is 50. Okay, minimum cost is 50, but you have to keep in mind that minimum 10 rupees are required for component A, that is component considered earlier, right? So your till 50 you will be putting a dash. Suppose say you don't put a dash here, but you may write point 0.8, and then you will be doing the computation for remaining value of the state, and you will find that remaining value of state is 0, and then you will be referring to the previous iteration for finding the optimal return for 0 state. You don't have it there, so if you don't have it there, you have to write dash here. Okay, if you are not forgotten there, okay, you have not taken there, okay, that is the case here. So minimum state whereafter, minimum state whereafter the returns are to be written are point 0.8, point 0.8, point 0.8, and this also should be this should also be point 0.8 and point 0.8. Okay, point 0.8 and point 0.8. Right? There is no why these were taken point 0.7 and point 0.8. You just be conventional. Okay, you write point 0.7 and point 0.7, and the next component here will be point 0.9, point 0.9. Here it will be point 0.8, point 0.8, and then point 0.9, point 0.9. Okay, point 0.8, into point 0.9, point 0.9. Okay, so the resultant values are resultant reliability that's coming like 0.56, 0.64, 0.72, 0.72, 0.72. Okay, and then optimal return you are getting here. Okay, so if you think you have 30 rupees, the reliability with just two components you can get 0.35. If you have 40 rupees reliability with just two components, you can get zero point 0.4, then 0.49, then 0.56. I am taking the highest value in each of the state row. 0.64, 0.72, 0.72, 0.72. Okay, I once again request you to consider here zero point 0.7 into zero point 0.9, zero point 0.7 into zero point 0.9, here zero point 0.8 into zero point 0.9, zero point 0.8 into zero point 0.9, and so. All right. Then coming on to last stage. Okay, here you see. Probably yes, because I have reached to the last component C. So far, my circuit is designed to contain component A bank and component B bank. Right now, component C bank, I am trying to insert. Okay, now once again going up and finding what is the minimum amount required to have a working circuit for which will be containing all the three components. Okay, so just look here. We'll be considering 1 unit of each of the component, right? 10, 20, and 20. So minimum 50 rupees will be required minimum. So your states now will be starting from 50 rupees ahead. There is no point in having the states from 10 to 40 and then 50, 60, 70, because you won't be having the values in you won't be having the values in the rows for state 10, 20, 30, 40. Even if you take those states, you will not have all the values there. Okay, anyway, so coming ahead, just a minute. Okay, now alternatives once again. C, 1 unit bank of component C cost rupees 20, that is given to you in the problem, and reliability is zero point 0.6. 2 unit bank cost, this is the number of units in the bank, cost rupees 30 and reliability is zero point 0.7, and 3 unit bank cost rupees 40 and reliability is 0.9. These are the alternative numbers 1, 2, and 3. The first entity in the alternative description is number of units in the component bank. All right. Now, if you have 50 rupees, If you assume that you have 50 rupees, you will be consuming, if you want to use this alternative, you will be consuming 20 for this alternative, and you will be getting the reliability of zero point 0.6. Okay, so for any amount which is greater than 50 rupees, you assume you have, okay, you are able to choose this alternative, and because you are able to choose this alternative, first component in the return is coming out to be zero point 0.6. Worry is about second component. So second component is found by taking the difference between the state and the alternative consumption due to alternative, right? So um, so 30 rupees, within that 30 rupees, you are having the optimal return of 0.35. Then here the gap will be the amount remaining, remaining value of the state. Okay, here will be 40, 60 minus 20, 40, and optimal return for that is zero point 0.4. Likewise, then for 50 rupees remaining, optimal return is 49, then 0.56, then 0.64, and 0.72 for the remaining amount, remaining value of state of rupees 80, that is 0.72. Okay, probably it was thought that these states won't be needed in my next analysis, so probably these values were not found out. But you don't take that liberty of avoiding certain calculations here. You complete the calculations. Okay, then second alternative won't be available to you until you have, now see, this requires 30 rupees. Okay, so 30 rupees, and this will be consuming 30, and in the previous stage you have the minimum state 30 rupees. Okay, so 30 plus 30, 60. So your state must be starting from 60 rupees for second alternative, right? Because if you take this won't be available this here you have written dash, because if you assume that you have 50 rupees, 30 are gone for second alternative, you are left with 20, and 20 is not available here in the previous stage. Okay, so if the alternative, if the optimal return for certain value is not available, okay, then you have to write dash there. So 60 rupees. You will be left with 30 rupees if you use this alternative, and for 30 rupees, optimal return is 35. Okay, means in 0.35, component B and component A together will be giving you optimal reliability. 0.35, then you know the reasons for having this 0.4, 0.49, 0.56, and 0.64. These are the optimal return for the remaining value of state, which comes as a result of state value and the consumption due to choosing certain alternative. So for example, 90 minus 30, 60, 60 rupees, you will have to find the optimal return for 60 rupees, that is 0.56. So here it has been multiplied by 0.56. Now this alternative once again will 40 rupees. This alternative you can use. Okay, but you need to have 40 plus 30, 70 rupees minimum. Okay, only after that this alternative makes sense, otherwise your circuit won't be having component B and component A. All right, so after you have 70 rupees, you can use this alternative whereby the return will be 0.9, first component, and second component, okay, will be 0.35, 0.4, 0.49, 0.56, right? And lastly, you find the optimal return. Zero point 0.6 into 0.35, 0.21, then zero point 0.6 into 0.4, 0.245, 0.315. Sorry, this is not point. This 0.245 is because of this. Zero point 0.7 into 0.35. Then another star which you are seeing here, this star is for connecting this with this, for associating 0.245 with this. That is not multiplication sign. Alright. Then 0.315 is because of this, 0.36 is because of this again, and 0.441 is because of this, zero point 0.9 into 0.49, and 0.504 is because of this. So maximum reliability which we can get if you have all three components in circuit and circuit is completed, then maximum reliability which you can get is 0.504, okay, by the components available to us, component banks available to us, 0.504. Okay. Now I want to design a circuit. For that I will have to backtrack. Designing a circuit means how many unit component bank is to be there. Okay. So, coming year, all right, I will be having this again exploded because something I need to explain on the page. All right. Answer part. Okay. Now 0.504 is the reliability. All right. Then first component means when you are backtracking, you are dealing with component C. So here I write component, then units in the bank, then cost, and then reliability. All right. Then component C I'll be writing first because that comes first when I start backtracking. Component C. Now 0.504 as you are seeing here, it is because of zero point 0.9 into 0.56, and that is because of third alternative which requires you to choose the component bank of 3 units. It costs rupees 14 and the reliability is zero point 0.9. This is all the data which I am picking from the alternative description. Okay, 350, 340 and zero point 0.9. Okay, now I started with 100 rupees, out of which I consumed 40. Okay, and now what is available to me? 60 rupees. Now for this 60 rupees, I will go with this 60 rupees, I will go to previous stage wherein there is consideration of B and A together. So in 60 rupees as you are seeing here, best reliability I am getting is 0.56, and that is because of third or second alternative. You choose any one of this at a time. So third alternative I'll be choosing. Okay, third alternative means for B component, that stands for using 3 units. Okay, and the cost of that is rupees 50, and the reliability is zero point 0.8. Okay, now out of 60 rupees I have consumed 50. 60 which was available to me at this stage, I have consumed 50. I am left with 10. Okay, I am left with 10, and in the 10 rupees I will be going to I'll be going to what stage, previous stage, right? So in previous stage, you are finding that in 10 rupees, you are getting the best reliability of zero point 0.7, and that is because of this first alternative. So first alternative wants you to use only one unit in component bank A. It will be costing 10 rupees and the reliability will be zero point 0.7. So total of the cost is 100 you are having, and this is 0.504. The product is 0.504. Okay. At this point, you might get another solution too. Like here, you will be getting. Okay, just look here. 0.56, I had another option in 60 rupees. I am writing that solution in red. Okay, you may or may not do it. Okay, here I could choose, as far as the first is concerned. There is no ambiguity. There is no that part is unique. Okay, and here the cost is 40 again. This is another solution I am writing, and the reliability is zero point 0.9. Then 60 rupees. Right. So, 60 rupees were remaining for products component B. And for 60 rupees, when we searched, the optimum return was 0.56. We have already considered this alternative as a part of second solution. Now we're considering this alternative, which requires you to have, which requires you to take two component bank for product C, product B, two component. The cost will be 40 and the reliability will be zero point 0.7, as you see from the top of that alternative. For 0.56, this is the alternative. And now after consuming 40 rupees from this 60 rupees, you are left with 20 rupees. Then you will come to previous stage, and in that previous stage you were finding that for 20 rupees the optimum reliability is zero point 0.8. All right. Optimum reliability. So 20 rupees means one component, sorry, two component bank. Cost is rupees 20 and reliability is zero point 0.8. So lastly, you have the cost here for second alternative, second solution 100 again, and the reliability is coming out to be 0.504. Both the solutions are written here. Okay, you may or may not find another solution. So we will stop here. Okay, and then another extension of dynamic programming in the continuous area, the we will be having another lecture for it. Okay, let's stop. Thank you.